Okay, let's get started. So thank you everybody for being here. And so today is another session of mastering generative AI foundation models for research. The topic that we're going to cover today is tool calling with LLMs. So I'm just going to have this presentation on present review. And as usual, I'm just going to walk through what's the motivation behind the concept. And then we will step into a Jupyter notebook in which we can see some examples of what you can do with tool calling. How does it work? And hopefully that'll give you some ideas of how can you leverage it from your own application building or research purposes. So let me first start by explaining what is this tool calling tool, like what does tool means on the concept of LLMs. I could say that tools or tool calling enables the LLMs to interact with external functions, such as web APIs or calling databases, such that the LLMs can expand their capabilities beyond pure text generation. So, as you are probably well aware of by now, when you are dealing with LLMs, like you you give text in and you get text out of it. So you can do a lot of powerful stuff, but with text. So in reality, an LLM or a language model, it's in general text generation machine in which it'll predict what is the next word or complete a phrase, and then you can start building up on top of it. Um, of course, if you have multimodal LLM, such as a vision language model, you can also pass an input image and ask questions about it, or use it as an alternate modality. But in the end, you get some sort of content generation, and that's it. It's not really a programming language per se. But what LMs can do is that they can follow instructions and come up with action plans, such that if they theoretically could be able to interact with their environment in some way, form, or shape, um, they could do like drive the control flow of a computer program. So they could be think of them as robots where tools are the limbs and the LM is the brain. So how they do this? Well, instead of merely producing next token, uh, the LMs can instruct something that can be parsed in real time to create information or execute computations or manipulate any sort of data in a structured way. So in a sense, if you put together a tool belt and bind it to an LLM, you get something that is more powerful and reliable and useful for a much wider range of applications. So that is like the overall concept. Where is this being used for? So tools are have a wide adoption in information retrieval and research assistance. For example, you could fetch real-time data from multiple domain databases. Like you could get the stock prices. You could create a database. Like last week, we showed an example. Um, you could like go into a corpus of legal information and find stuff that doesn't necessarily exist within the parametric memory of the LLM, but we can retrieve it. So you've heard a lot probably already about retrieval augmented generation. So tool calling is like a generalization of this concept because in retrieval augmented generation, you query a vector database to get text related to your question. But in tool calling, you abstract away that vector database into whatever you can encapsulate within a source code function. You basically define a Python function, and this could be program control or the vector database itself, etc. Tool calling is also used for automation and productivity. For example, executing those SQL queries or there are applications that like you could build an assistant such as Siri or the Google Assistant or Cortana, in which it can manage your calendars or automate those workflows because an operating system or an development platform exposes that functionality as APIs. It can also be used as chatbots. Why? Because sometimes, like if you have a chatbot, it is not uh, well defined. What does the user wants to do if you interact directly through natural language? So if I'm trying to contact a service representative of a company, I might phrase it in 1,000 different ways, and you cannot really hard code it efficiently, but the LLM is able to distinguish that. So the LLM might route the control flow of that chatbot to call the appropriate functions or handlers. It's also used in healthcare to assist triage or to help with summarizing stuff. Like if it could be as an assistant for healthcare, and basically everything that you can think of that you can code, but as an API. So an LLM with tool calling can become a generalized program that you can command using voice or text. So um, what does this can be used for in general? This is the aha moment or light bulb. You could use it to create AI-driven application development, which is pretty cool. And I must tell you that if you've been looking at the job market for the last probably 6 months, um, most of the vacancies right now are related to some sort of AI agents. So we're going to explain a little bit more about those later today. But it's an AI agent is a generalization of using tools with LLMs. So in its most fundamental way, tool calling is just allow an LLM to call a function. But you can create an agent to build applications with it. So that's enough theory. So how does this work? There are many ways to use LLMs, but you can compel them using your prompts to call those functions. So you're going to start from a notion that you have a function that is able to perform a specific task, but you're not the LM. You as an LM wouldn't be responsible for running it, just to command something else to run it and give you back the result. Um, so initially, people figured it out that they could prompt engineer their way into commanding the LMs to command another platform. But then eventually, like this became a widely use case in which those LMs uh, were fine-tuned using supervised learning and reinforcement learning to actually do that. So a lot of data sets that for this are available. Just to give you a peek of how this could look like, um, you will get you need like when you're fine tuning an LLM, you need examples like inputs and expected outputs. So what if you're asking a question, what is the weather in New York? Of course, an LLM can hallucinate it and give you a fake number that might be by chance correct, but it can do better. So whenever it sees that it can interact with something, it'll output a function name and its parameters. So there's a function called getWeather, and you need to specify where you want to get the weather from. So this could be New York, could be your coordinates with latitude and longitude. I don't know, a specific region or a state, whatnot. But that doesn't really matter. So the important part here is that we get an input with a command, and as an output, instead of getting a textual response, like saying something that was hallucinated or taken out of the context from prompt, we get a function call. And that function call is going to be comprised from a function name and a set of arguments. So the arguments are name as well, like location, New York. We could be more complex. We could go more complex than this. Like a function could have multiple inputs, or there could be multiple functions that have to be called in order to answer this question. So by fine-tuning the LLMs with datasets that look like this, we can teach these LLMs how to generate these structured outputs that can be parsed with a computer program to actually call those functions. So one key insight here is that if you see here the output, it is a JSON object, or it is written as a JSON object, which is a bit of a structured data. So it is basically a like JSON parsers are a commodity, if I may say so, in today's programming languages. So you can take that string and parse it into a dictionary or a map or whatever JavaScript object equivalent representation you can use in your programming language. If this is Python, it's a dictionary, and we have expected keys with their values. So we can easily parse that and then just dispatch the function to its appropriate handler. So how could that look like with an LLM? Say that I want to actually get a piece of code that implements this. Okay, let's use LangChain for that, because just for consistency, LangChain already has this notion of tools included in itself, and this is how it could approximately look like. We're going to see a live example, but for now, let's just look at this. First, we need the actual tool. So we'll define a dummy function called fetchWeather that has a parameter location that's a string. It'll return string. Could be a floating number if you want just the temperature, but let's say that we are appending the condition, like the weather condition, and its temperature. So here this is in Celsius, but I can tell you that this is like pretty comfortable. What we're going to do is that if the location is within this dummy database of weather data, that means if we ask for New York, London, Paris, or Paris, we're going to return it. Otherwise, we're going to return location not found. This is just to prove the point. So this is a standard Python function, nothing special out of it. But we need to be able to bind it to the large language model. So with LangChain or Llama Index or OpenAI API, usually you'll have the constructs or the classes to do this. So LangChain uses a Pydantic model that describes the tool. So we'll create a weather tool Pydantic model that has a name, a description, and a pointer to that function. So the name of the tool and the pointer to the function, I don't have to say a lot about it. It is pretty obvious. Like this tool is going to actually call the fetch weather function. But what I want to bring to your attention is that the description is crucial when you're using tools. Why? Because you can, it's as if you were a programmer using an API. Like you can read this and infer what it does, but a well-developed API is going to have documentation, and that documentation is going to clear any ambiguities that might be present in there, like maybe the idiosyncrasies about how to use this API. So the description is the same for us and for the LLM as well. So the description here is that this tool fetches weather information for a given location, which kind of be obvious for us, but maybe not for an LLM. But if we had a lot of parameters, it could be beneficial if we could document each of the parameters here and specify what was their data type and what it is meant to control within that function. We can also add more than one tool. So think about this calculate sum. That it's pretty much the same. It's going to return a string that spells out what is the summation of A and B, and it's going to perform the arithmetic itself. Yes, I'm going to increase the font. Make it a little larger. Is that better?
Yep.
Thank you. Okay, so again, we do the same thing. We create the function, we create the tool object, and we can do like return a random joke. This doesn't take any parameters. And that is it. That's how we create tools. Then we need to bind them to the LLM. I'm going to show you how on the live example. And the workflow looks like that. Once we have those tools, let's call them that set of tools. Let's call them tool belt, just to follow the model or the abstraction. We're going to bind them to the LLM. Bind them to the LLM. The LLM is going to know that it has tools available because the way these LLMs have been trained is to recognize when they have tools. So if they recognize they have tools, they're going to call them when they think that it's needed. So the LLM is going to tell us, you know what, like based on what you asked, I need you to call these tools for me with these specific parameters. So we're going to get that back from the LLM. And us as software developers have to execute those calls and retrieve the results. Once we have those results, we're going to add them to the conversation and send it back to the LLM. Then the LLM is going to be able to reply or answer the question that we asked. So let's stop with the theory and let's look at the practice. Give me just a second. So let me sharing my screen here. I'm going to make this bigger. So if you're familiar with LangChain, most of these will be already known to you, but let's just walk through it. The first thing that we have to do is that we need to create a handle to the LLM API that we're going to call LLM. So we specify a model, we specify an API key, a base URL. So if you're using OpenAI, most of these will be pre-populated for you. But if you're using AI Birdie, you have to specify what's your API key also in a different base URL or a different model name. But so far, this is standard. So let's run this. I usually like to do a test call with hello, just to make sure that we set it up correctly. And yeah, hello, how can I assist it? How can I assist you today? And today I'm using GPT because it's easier to make the point of how to works using OpenAI, but this also works with Llama or with Quen or other open source LLMs. So this is a plain call to the LLM, but we want to work our way up towards binding a toolbelt with the LLM. So first, the first thing we have to do is that instead of just calling hello, we want to set the role of the LLM. So we're going to create a conversation that has a system message. So a system message primes the LLM with whatever it's supposed to do. So you give it context based on the system message. Therefore, we're going to say that you are an assistant and you have tools at your disposal to help a human achieve some tasks. Each time that you're calling a tool, think out loud what you're doing and what you're doing it. Then I'm going to like pass a question or a query. So this is a placeholder. So using LangChain, you can get this prompt template. Then we're going to define one tool just to make this up, to make an example. So I want to create a calculator tool. This calculator tool is going to take two operands and an operator. It's going to compute something with it. So that something can be any of these four basic arithmetic operations: addition, subtraction, multiplication, and division. And this is like pretty standard, right? Like add something. Instead of having a separate tool for each operation, we have a calculator tool that takes an additional parameter that specifies what is the actual operation that we want to execute. So, we just switch depending on the operator and return the appropriate value. If the LLM is asking for something that is not supported, like if we want to elevate a to the power of v. That's not supported here because it's not implemented. So we're going to raise an exception out of it. And if you read this, it might be easy to figure out what's going on here. But we can lend a hand to the LLM. And we can do that through the docstring. So this is Python, and the docstring is supposed to document what the function does. So we're going to say, like, this is simple calculator function. Not for real-sided, right? We don't have to elaborate anything else because it's really that simple. But we need to specify, like, what are the arguments. A is a float argument, which represents the first operand. Decode B, but for the second operand. And the third argument up is the operation to perform. We are specifying that it is only supposed to execute this. So this is string, and the LM, if the LM reads this, should know how to call the calculator. It returns a floating value, which is the result of calculation, and raises this value error. So this is like a comprehensive documentation for an almost trivial function. How can we expose this to the LM? Well, we can create that tool object that I showed you in the previous slide, or we can take a shortcut and we can use this tool decorator. Tool decorator is just like syntactic sugar that uses the reflection system of Python to build that instance of the tool object, such that we can use it like with the LLM. So we're doing that. You can see that we are importing it from LangChain. And let me run this. Okay, and then we're going to do the actual bind of the tools. So we had a handle. Let's spend just a minute on this cell. LLM is a handle to the LLM model through the API. But we haven't said, although we are going to specify on the system perm that it has tools, we haven't said which tools it has. So we can bind the tools, which I have mentioned a couple times already, using this function, obviously. And we can specify which tools are available. So here, this is just a collection of options that have been decorated with the tool decorator or the two objects that I showed you on the slides. And tool choice is just an additional flag that you pass using the OpenAI API that allows the LM the freedom to decide whether it has to call a tool or not. You can require it to always call a tool, or you can ask it to never call a tool. Although I don't see why you would want to buy the tool belt and never call it, but that's the way it is. Once we do that, we get a new object that represents the same LM handle, but with the tools already bind. And we are going to then get the conversation. So we're going to ask for two things, two operations, 2 plus 2 and 3 divided 5. So let's call the LM and get the result and see what do we get out of it. Okay, so we already call it. And the actual output message is going to have tool calls. So since we've bound the tools to the LM is going to tell us back, like execute these tools with these argument values. And if you remember, I mentioned a couple minutes ago that the LM is going to give you a JSON object that can be parsed. Well, LangChain already does that for us. So it gives us, we didn't have to deserialize the JSON. Instead, we got those tool calls assigned into a field called like that have the name of the function that we want to call. Functional or tool is the same thing here. The arguments, so we have A is 2, B is 2, and we want the addition. And we have an ID. So the ID is just an identifier for this specific invocation of the tool. And likewise, we get another call to calculator with 3 divided by 5. And you can see why we need an ID here. because we're calling a tool, the same function, the same tool call twice with different arguments, granted, but we want to be able to tell the LLM back, when I run this invocation of the tool with this ID, this is the result that corresponds to that ID. So this is just a way to match together the input to the output. So far, we got the tool calls, but it is our responsibility as the developers to take these tool calls and actually do something with them. So what we're going to do is that in this auto cell, we're going to iterate through each of the tool calls and we're going to actually run it. So let's think about what's going on here. So we have two different tool calls. So we're going to consider each individually. But how do we know how to call it? Well, in this case, it's sort of trivial because we only have the calculator tool. But what we're going to do is that we are going to have a dictionary that has all the tools by their name. And the key of that dictionary is going to be the name of the tool. So we're associating the function that we created with its name through this identifier here. So what we're doing, what in this line, what we're doing is that we're selecting the calculator function. Once we have an additional function or an additional tool, you'll see how this comes handy. And perhaps you won't be as lazy as I am and just factor out that dictionary to have it once outside of the loop. But we have a pointer to the chosen tool. So once we have that pointer, we're going to call invoke with the actual tool call. So you may be thinking like, what is this invoke method? Why is there a method if calculator was a function? Well, what happened here is that when we decorated the calculator function with this tool decorator, in reality, what happens behind the scenes is that we create an instance of an launching runnable that contains this invoke method and expects the actual tool call such that it can wire together. Like you don't have to specify the arguments nor the ID. It'll pipe it through for you and run the function inside of it. So that result is going to be marshaled into a tool message that goes into a conversation and is going to be appended to the conversation. So if we run this loop, what's going to happen is that we're going to have two iterations, and we're going to have as a result of each iteration a tool message that contains the result. So if we inspect at the actual conversation in this messages array, we have first the system message that we specified, the human message that was our prompt to the system. So as a result of this prompt, the LLM told us, it didn't tell us like anything through its voice, its inner voice, I guess, but it told us that, you know what, you have to call these two tools. We collected that result, we executed those functions associated to the tools, and created tool messages that contain the result. So you can see here how 2 plus 2 is 4, obviously, and then 3 divided by 5 is 0.6. And you can see how in this tool message we specify the pointer to the ID of the tool. So the LLM is going to be expecting this because it was trained to match the results of the tool to its invocations through the ID. So once we have this new conversation, we're going to send it back. Remember, the LLMs are stateless, so you have to send the whole conversation each time that you append the message. So we're going to send that, and then we're going to print the result. So the result of 2 plus 2 is 4, and 3 divided by 5 is 0.6. So what is important about this? So just take a pause and think about what happened here. We could have asked this to the LLM without using tools. It might very well have given us the correct answer because maybe it's able to figure it out on its own by predicting what's the next token. So it's most likely that it has seen 2 plus 2 equals 4 on the string data set much more times that with an incorrect number. But we didn't want to do that. So when you're using LLMs, you don't want to delegate um, computations that can be executed exactly using standard computer programming to the LLM, because you're always running the risk of getting a hallucination. Instead, you want the LLM to behave as an orchestrator. So it'll have these options available to execute something, and then your computer will execute it. So in my own computer, I executed these two calculations. Once the LLM got the result back, it'll spit it out. So it'll give you this message. And you can repeat this. So if you put this into a loop, that becomes an agent, basically. Um, but so far, this has been a trivial example, right? So what if we can do something more useful? Like there are some predefined tools on LangChain and or other frameworks such as Brave Search. So Brave is a search engine, a competitor to Google. And the only reason I chose this is because it like you can create an account for free and do web searches with it. So what we're doing here is that I'm passing my API key. So you can go and register. It'll ask you for a credit card number, but it's not going to charge you anything. And because it's throttled, and you have a maximum number of requests per day, I guess. But for the sake of the workshop, this is okay. So we pass some parameters to search um, the search engine. Like we only want the top two results. So if we run this tool, like we're not running the LM, instead like we create an instance of the Brave Search tool, and I want to see like what is out on the web about me. So I put in my name. I see like the first result is my Google Scholar profile. It has a snippet, and then a semantic scholar profile, which is pretty similar. Like ResearchGate. I guess it's pretty clear that I'm an academic by doing a Google search. So the LM might as well know these two, but say if I pivot my career and create something new that hasn't been part of the training data, um, it won't know it. Like until it's retrained with the latest version of their data set. So instead, like yes, let's enable the LLM to also be able to carry out web searches. So we're going to follow the same recipe, right? We're going to bind the tool belt to the LM. In this case, we're going to bind the calculator with the, let's rename this. Well, no, it's not necessary. This could be web search, but whatever. So let's again ask it to do two different things. First, fetch the population of Tucson and then multiply it by 2.5. Hopefully, it'll pick up like it'll find a result, a web search that spells out what is the population, find out what is that number, and then call our calculator to multiply by 2.5. Okay, so I haven't sent it to the LM yet. Like this is just like the set of messages. This is the conversation that will go. Then I'll send it to the LM, like these two messages, and let's see what do we get back. Okay, first, it is picking up that the first thing that it has to do is to call Brave Search with this query: current population of Tucson, Arizona, 2023. Why is it asking 2023? Because somehow GPT 4.0 thinks that today's 2023. Doesn't really matter. No, we can prove it. So again, this is the structural representation of it. We're going to hold on. Yeah. We're going to call this Brave Search and say, see what do we get. Okay, so we have the population of Tucson in 2025. So this was helpful because the LM probably was trained in 2023. But by using web search, we're not relying on the parametric memory. Instead, we are actually going out and find out that the population of Tucson is this. And we have more stuff, right? Doesn't matter. So what we're doing is fetching information. Think about it as a recurrent augmented generation, but through a web search instead of a vector database. So we're going to send back this conversation to the LM and see what do we get now. Okay. So now the LM is telling us that the population of Tucson in 2023 is 1 million residents. So first of all, I think this is twice what the web search said. So there's probably a bug. It was sort of hallucinated maybe, or it might have been part of like the metro area population. We'll need to see what's the result of web search. But what is important here is that this was the first portion of our query. Now the LM has determined that it has to call a calculator to multiply it by 2.5. So we get this number derived out of the web search, and we got this from our initial query or initial prompt to the LM. So we want to multiply both. Let's do the same thing, right? We have one tool call, and see this, like system message or prompt, like initial prompt. The AI, the LM replied with a first tool call. We executed the tool and put the result back into as a tool message. Then we send it back to the LM. The LM gave us an answer, and then it's requesting another tool call message. We executed that, and we are about to send it back to the LM and see what's the result. The population of Tucson, Arizona multiplied by 2.5 is 2.7 million residents. So now you can see that you can start to build up more complex workflows. And so I think that so far, if the fact that we got to this point is pretty neat. Like it's really cool that we are able to make an LLM interact with its environment in an interactive fashion. So it's not just single tool call. Like it can call parallel tools, it can call serial tools, as with this example. But you can see how this becomes cumbersome. Like, what if like we want to generalize this behavior? And this is where the agents come in. So think about this. Like if I had to repeat a lot of code on the other notebook, but we can code loop that uses the LM itself to determine whether it has finished or if it has to go out, we'll call it another tool again. And that is the notion of an agent. So an agent is another whole topics. We're just going to cover it briefly in the last couple of minutes that we have in using this notebook. So again, we're going to create a handler to our LM using the test run. We're going to define our tools here. So for brevity, like I got search tool and the calculator tool. And then we are going to use LangGraph to create a React agent. So React agent is just the name of a method that someone came up a couple years ago that works really well because it is designed such that the LM receives a question and like does an introspection. Well, it does introspection, right? Like, but you ask it to pull its train of thought. Like, you're asking me this. I need to know these A, B, and C elements of information in order to be able to answer you. So I'm going to figure out each of those individually. And for each of those, it's going to call a tool or potentially 0, 1, or more tools. And once it goes through all of those and collects the results, then it's going to figure out if it has to do something else. If it's finished, then it'll give you a response. Otherwise, it's going to call the tools again or ask you for a clarification. So Memory saver is just a way to store the intermediate, like the intermediate steps of the conversation, because it thinks itself internally. But what we're going to do is that we're going to call the create React agent with the handler to our tools. We didn't have to bind them manually because this happens inside the function. We pass in tool belt the check pointer. So our tool belt again is just the calculator and the Brave search tool. So then I can actually pass an input message. So we're going to use a stream such that we can start like stream back the response instead of waiting for it to finish. And then we can inspect the actual intermediate steps. So first I'm going to say, I am Enrique. I live in Tucson. Um, yeah, it's not calling a tool because like, I didn't ask for anything yet. And it's asking like, what can I do for you today? Okay, so I want you to search for information in Google Scholar about my research publications and then add up the total number of citations across all of my publications. So I'm like, this is vanity, right? I want to show off. Like I want to show that I have citations. So but I'm too lazy to go out and count them myself. So let's get the LLM agent to do that for me. So first of all, I didn't specify again that I am Enrique. It already knows that because when we created the agent, we got a memory saver. So the conversation is stored. So once we ask for this, we start right after this AI message. Um, okay, but now like I gave it a concrete command that it has to go out and execute. So the first thing is that it has to search information in Google Scholar about my research publications, etc. So yeah, it can go to Brave Search and specify, this query term on this site's Google Scholar, and it'll get this response. It'll execute the tool for ourselves. So this is already programmed in such a way that you don't have to code it yourself, but it gets the tool message. Uh, I wonder, like, if it knows about it, about my number of citations. This is not me, so this is the second result, I guess. Okay. Now it didn't get it right, so that's one of the benefits of the agents. They're able to figure out if they didn't get the result and try it again with a different search term. Um, okay. So it went out and it found that I have 186 citations. I wish they were higher, but like something. But this it didn't go enough. It didn't do enough. It didn't do as I wanted. So it was able to get this number out of research instead of like getting each individual. Um, so I wanted to use the other tool as well. So what if I ask it to execute, like divide those by 12? Like this is just a toy example, but it figured out that it has to call the calculator. It knows about my 186 citations as of today. Again, this is embarrassing because I thought I had more, but whatever. Divided by 12, and the number is 15.5. And the total number of citations is 86. So, like, the effort to do this in terms of programming was significantly less than in the other notebook because we took that notion of tool calling one step above and we actually used an agent that, like this is so popular right now that there's like, you'll find dozens of agent libraries out there. This one is nice. It works really well with GPT and with Llama and Quencoder. But this is a highly hot research area. So, I bet that a month out from today, there will have a nicer tool that works even better. So let's go back to the slides to wrap this up. Uh, we can wrap this up by considering the following highlights. First is that the LMs can only generate text, and this is besides the star because that text is not necessarily text. Could be images, could be speech, audio, depending on the modality, or a mixture of those. But they do not execute like they're not a code interpreter. They're just a media generator. But tool calls is a paradigm to request external information into the LM, into this conversation, such that it can do something more useful than just hallucinating stuff. Models are explicitly tuned to issue 0, 1, or more tool calls to elaborate its final response. And once we master tool calling, we are one step before being able to build LM agents, which are the cornerstone of AI-driven applications, like contemporary AI-driven applications. So with that said, I think we've finished today, and I hope that you liked it. And I am around a couple of minutes in case that you have any questions.